Let's elucidate the oracle in the quantum search algorithm. The oracle omega distinguishes targets from non-targets. The targets are elements of the set T. The non-targets are not elements of the set T. Both the targets and the non-targets are all elements of the set G. The set T, which contains all of the targets, is a subset of the set G. In total, there are C targets, and there are n minus C non-targets. N is the cardinality of the set G, which is 2 to the power of L, where L is the number of qubits in our register. 2 to the power of L is the dimension of the Hilbert space that describes a register containing L qubits. C is the cardinality of the set T. We can think of C as the total count of all of the targets. We need C to be less than 1/2 of n. Let's consider the ratio of C and n. We're going to use that ratio to define the angle theta. By convention, we're putting a factor of 1/2 in this definition. So 1/2 of the angle theta is defined as the inverse sine of the square root of this ratio. Alternatively, we can define 1/2 of the angle theta as the inverse cosine of the square root of 1 minus this ratio. So we're turning this ratio of C over n into an angle theta. And the reason we're defining this angle is because we want to use it to express coefficients in a linear combination. Let's examine this quantum state. We can prepare this quantum state by first initializing an L qubit register in all zeros, and then applying Hadamard gates to all L qubits in this register. When you see a 0 labeling a ket with a superscript L, that is shorthand notation for an L qubit computational basis state that corresponds to initializing in all zeros. So that means all L qubits in this register are initialized in the single qubit computational basis state labeled by 0. After initialization, we apply Hadamard gates to all L qubits in this register, and that is shown with this H with a superscript tensor product L. We can think of this as a multi-qubit Hadamard gate acting on the entire register of L qubits. So this produces the state which is labeled by a plus. So we have plus labeling this ket with a superscript L. And this plus state is shorthand notation for a uniform superposition of all of the L qubit computational basis states. How many L qubit computational basis states are there? Well, it's 2 to the L, which is the same as n. That explains this normalization coefficient of 1 over the square root of n. And what are we using to label these states? We're using these little g's. These little g's are elements of the set G. And we can express these little g's in binary notation as L-bit strings. And they serve as labels for these L qubit computational basis states. And again, we have a superscript L to remind us that these are not single qubit computational basis states. They are L qubit computational basis states. And we're preparing a uniform superposition of all of them. So we're summing over all of these elements of the set G. And later in the video, we're going to do some algebraic manipulation that justifies this relationship. We can break this uniform superposition of all of the L qubit computational basis states into a linear combination of the orthogonal superposition and the target superposition. These are defined in this blue box below. The target superposition is a uniform superposition of all of the target states. So the target states are L qubit computational basis states that are labeled by these little t's. They are labeled by the elements of the set T. And you can write these little t's in binary notation as L-bit strings. And those L-bit strings serve as labels for these target states. In total, there are C of these L qubit computational basis states that are target states. C is the cardinality of the set T. It's the total count of all of the targets. So we want to measure these states. We want to measure the target states that are present in the target superposition. The goal of the quantum search algorithm is to amplify the amplitudes that are associated with these target states. What about the remaining L-qubit computational basis states? We don't want to measure them. We want to minimize the amplitudes associated with those states. And we can combine them and put them into an orthogonal superposition. And this is called the orthogonal superposition, and we're using this perpendicular sign to label this state. This is also a uniform superposition, but it only includes the non-target states. And those are labeled by these little h's. And these little h's are all of the elements of G that are not elements of T. So you can see that H is not an element of T. And we're summing over all of these h's. So these are the non-targets. And in total, there are n minus c non-targets. That explains this normalization coefficient of 1 over the square root of n minus c. So that's the target superposition and the orthogonal superposition. And over here we can see a linear combination of these basis states. We're actually going to treat them like a basis. We can call that the target basis. So we have a target superposition and an orthogonal superposition. And the coefficients in this linear combination actually depend on the ratio of c over n. And because we've defined this angle theta, we can change this from depending on the ratio of c over n to depending on the angle theta. And over here we have cosine of theta on 2, and here we have sine of theta on 2. So this is a very convenient way of expressing this quantum state. So we're expressing it as a linear combination of a state that we are interested in and a state that we're not interested in. So we have the orthogonal superposition, which contains all of the non-target L-qubit computational basis states, and then we have a target superposition, which contains all of the target L-qubit computational basis states. Now let's have a look at what the oracle does to these basis states. So for all of the elements of the set G, if we use those little g's as labels for L-qubit computational basis states, and then act with the oracle on those L-qubit computational basis states, we're going to get a phase factor being multiplied out here. And that phase factor is -1 to the power of this function f. And this function f is turned off for non-targets, and it's turned on for targets. So we can see the two cases down here. So for all of the non-targets, those are the elements that are the elements of G that are not elements of T, the function evaluates to 0. So if we put these h's inside of the function, we're going to get 0. And that means we're going to have -1 to the power of 0 over here, and that's going to give us +1. So the oracle doesn't do anything to these states. It just leaves them alone. It gives them a +1 coefficient, which is the same as the identity operator. But the targets are different. For the targets, this function gets activated. It gets turned on. So if you put these targets inside of the function, then the output is 1. And so you get -1 to the power of 1, which gives us a -1 coefficient. And we can think of this -1 as a phase factor. We're introducing this phase factor onto the target states. So this is how the oracle omega acts on L-qubit computational basis states. It distinguishes the non-targets from the targets. How does it do it? Well, it marks the targets with a phase factor. And here we're using the phase factor of -1. So how would the oracle act on the orthogonal superposition and the target superposition? Well, the orthogonal superposition only contains these non-target states. That means we're just going to have a plus sign over here. So there's not going to be any minus signs introduced. But the target superposition, it contains all of the target states, and they're all going to get marked with a minus sign. So that means we're going to have a minus sign out the front of this target superposition when the oracle omega acts on it. So you can see that this is how we're going to mark the targets of search. So it's a way of distinguishing the states that we're looking for from the states that we're not looking for. So that's what's happening in this red box over here. And now let's have a look at the bottom part of this blue box. We can see some notation for the target projector and the orthogonal projector. The target projector projects onto the target subspace. The orthogonal projector projects onto the orthogonal subspace. You can see on the left there's a shorthand notation, and then on the right we have a full summation notation. We're summing over all of these ket-bra combinations, and all of these ket-bra combinations are constructed from the target L-qubit computational basis states, and we're summing over all of those little t's, which are elements of the set T. So that's how we produce the target projector. And the orthogonal projector is produced in a very similar way. We're just summing over all of those h's, which are not targets. We're summing over all of the non-target states. And we're using those non-target states to construct ket-bra combinations. Now let's have a look at the purple box. We can express the identity operator, which is denoted by I sub 2 to the L, and this 2 to the L specifies the dimension of the Hilbert space. So we can express this identity operator as a sum over all of these ket-bras that are constructed from all of the L-qubit computational basis states. So we're summing over all of the elements of the set G. And we can break this sum of ket-bras up into two parts. We can break it up into the non-target part and the target part. And then we can identify the orthogonal projector over here and the target projector over here. And then we can write it in shorthand notation. So here's the shorthand notation for the target projector and the orthogonal projector. So we're just splitting up this sum, and we're identifying the ket-bra combinations that are constructed from target states and the ket-bra combinations that are constructed from these non-target states. Now let's try and express the oracle in terms of these ket-bras. So we can define the oracle as the identity operator minus 2 times the target projector. And because we've already seen that the identity operator can be written as the sum of the orthogonal projector and the target projector, we can cancel out one of the copies of this plus target projector with one of these minus copies of the target projector, and that just leaves one copy of minus the target projector. So the oracle omega is the orthogonal projector minus the target projector. And we can write this out in this full notation, so not using this condensed notation. Here we see a representation of the identity operator, and then we have 2 times the target projector, and that's the same as this orthogonal projector minus the target projector. So here we're writing it out in full. We're writing it in terms of these L-qubit computational basis states. And those L-qubit computational basis states are being combined in these ket-bra combinations. And that's what's being used to construct these projectors. So this purple box gives us some information about how we can express the oracle omega. So now we've introduced many properties that are used to describe the oracle omega. Next, we're going to have a look at some algebraic manipulation which justifies this step over here. Why are we allowed to break up this plus state into a linear combination of the orthogonal superposition and the target superposition? We're going to see some algebra that justifies this. In this blue box, we can see different ways of expressing a uniform superposition of all L-qubit computational basis states. The first two expressions indicate how this uniform superposition is prepared. First, we need to initialize a register of L qubits in all zeros. Then we need to apply Hadamard gates to all qubits in the register. Have a look at this purple box. This purple box shows the quantum state of the L qubit register immediately after initialization, so before we apply the Hadamard gates. On the left, we can see a notation that emphasizes individual qubit states. On the right, we can see a condensed notation for this L-qubit computational basis state. The first expression in the blue box emphasizes individual qubit states. So we can see single qubit computational basis states that are labeled by 0 being acted on by Hadamard gates. This second expression uses a more condensed notation. And this third expression is the most condensed of them all, because we're just using a plus as a label for this ket and then we're putting a superscript L at the top to remind us that this is a uniform superposition of all L-qubit computational basis states. Let's have a look at this expression over here. We're summing over bits. So all of these values that are indices in these sums, they are bits. They can be either 0 or 1. And we're actually summing over all of the bits that form an L-bit string. So this L-bit string, shown in the green box at the top, is a binary representation of an element of the set G. And the set G is actually the integers mod 2 to the L. So we're constructing a binary representation of this element, which is an L-bit string. And each of these bits can be either 0 or 1. That gives us 2 options. And because we have L bits, that gives us 2 to the L options. 2 to the L is the dimension of the Hilbert space that describes an L-qubit register. So that explains this normalization coefficient of 2 to the power of minus L on 2. So this normalization coefficient can be rewritten as 1 over the square root of n, because n is 2 to the power of L. So n is actually the cardinality of the set G, and n is also the dimension of the Hilbert space. And it is also the number of L-qubit computational basis states. So in this format over here, it's far more condensed. We're just summing over all of these little g's. And these little g's serve as labels for L-qubit computational basis states. And we have this superscript L to remind us that these are not single qubit computational basis states. But if we go back up to this big expression, we can see the individual qubit states. And we can also imagine tensor product symbols in between. So we're going to use the tensor product to combine all of these single qubit states into an L-qubit computational basis state. So G sub L minus 1, G sub L minus 2, all the way down to G sub 1 and G sub 0, these are bits. And they're either going to be 0 or 1. And they are going to label these single qubit computational basis states. So we have all of these L bits that we need to sum over. That explains why we need all of these sums. But alternatively, we can just write a single value G. And this value of G is what's being summed over here. So these are 2 different ways of expressing this uniform superposition of all L-qubit computational basis states. Now let's have a look at this sum and split it up into 2 parts. So we're going to split up all of those L-qubit computational basis states into 2 categories. We're going to have the non-targets and the targets. The target states are L-qubit computational basis states that are labeled by these little t's. They are elements of the set T. And the h's serve as labels for the non-target states. The h's are elements of the set G, but they are not elements of the set T. So we're just classifying the L-qubit computational basis states based on what label is being used. So here we have the non-target sum, and here we have the target sum. If we multiply and divide by some factors, we can actually identify the definition of the orthogonal superposition and the target superposition. So those are the superpositions that we defined earlier in this video. And then we can write them in this condensed notation. So we have the perpendicular sign, which is the label associated with the orthogonal superposition. And we also have this T, which is the label associated with the target superposition. And we can change this over here. We can identify that we have n divided by n. That's the same as 1. So that changes this coefficient. And that gives us this linear combination. And we also introduced the angle theta, which allows us to turn these coefficients into these coefficients, which are written in terms of trigonometric functions. So this coefficient of the square root of 1 minus the ratio of c over n, that is the coefficient of the orthogonal superposition in this linear combination. And the square root of c over n is the coefficient of the target superposition in this linear combination. And we can just rewrite them in terms of the angle theta. So then we get cosine of theta on 2 and sine of theta on 2. If we were to take the inner product of the target superposition with this uniform superposition of all L-qubit computational basis states, then we would actually get sine of theta on 2. And we can see that in the red box. So over here we have an inner product. We're taking the inner product of the target superposition and this plus state. So the plus state is just shorthand notation for the uniform superposition of all L-qubit computational basis states. And here we have the bra version of the target superposition, and then we have the ket version of the plus state. So we're summing over all the t's in this bra version, and we're summing over all the g's in this ket version. And we can pull out these normalization coefficients and combine them into one. We have 1 over the square root of n times c, and that gives us two sums. We're summing over all the t's and all the g's, and then we have an inner product. So we have a bra version of the little t, and then a ket version of the little g. So we're taking an inner product, and all of these L-qubit computational basis states, they are orthonormal. We have an orthonormal basis. So that means that they are normalized and that they are mutually orthogonal. So we're only going to get a value of 1 over here if t and g are the same. And we're going to get a value of 0 if t and g are different. So that means that so let's consider over all of these t's, there's only going to be one g that matches this specific t. So if we consider just one target in this sum, there's only going to be one possible value of g that matches that target, and that's going to give us a 1 over here. So we're only going to get one contribution for each of these targets. And how many targets are there in total? Well, there are c targets. C is the cardinality of the set T. It's the total count of all the targets. So this evaluates to c times 1, which is just c. And then we can pull that c inside of the square root, and it turns into c squared, and then we can cancel the c downstairs, and that just leaves us with a c upstairs. So we get the square root of c over n. And this quantity is the same as the sine of theta on 2. That's just how we defined the angle theta. If we were to take the inverse sine of both sides and then multiply by 2, we would be able to isolate the angle theta. So that is the inner product for this target superposition. Now let's do the same thing, but for the orthogonal superposition, which is denoted by this perpendicular sign. So now we have a bra version of the orthogonal superposition. We can again combine these two normalization coefficients into a single normalization coefficient. So we have 1 over the square root of n times n minus c. And then we have these two sums. Here we're summing over all of these h's, which are non-targets, and we're also summing over all of the g's. And then we have this inner product. We have a bra version of this little h, and then we have a ket version of this little g. So this is only going to be 1 when h and g match, and it's going to be 0 otherwise. So it's very similar to what we had in this format up here with the target inner product. So let's consider a specific non-target, so a specific value of h. How many g's are going to match? Well, it's just going to be 1. There's only going to be one g that matches that specific value of h. So we're only going to get 1 from one of these values. And how many non-targets do we have in total? Well, it's n minus c. So we're going to have n minus c copies of this evaluating to 1. And all of the other inner products of the L-qubit computational basis states are going to be 0. That's because they are an orthonormal basis. So then we get n minus c times this normalization factor, and we can bring that inside the square root, and we can cancel that factor of n minus c in the bottom, and that leaves us with the square root of n minus c divided by n. And we can actually split this up into two fractions, and we can identify that it is the same as this coefficient over here. So when you have n divided by n, that's the same as 1, and then we're just subtracting off this ratio of c over n. And this is the same as the cosine of the angle theta on 2. And then we can take the inverse cosine of both sides and multiply by 2, and that's going to allow us to isolate the angle theta. So this blue box has provided us the algebraic justification for how we're allowed to break this plus state up into a linear combination of the orthogonal superposition and the target superposition. Now we're ready to move on to construct a geometric visualization. And in the next video, we're going to construct a geometric visualization of the quantum search algorithm.